All right, so we're going to look at what's called proof by induction. It's a very powerful tool in maths, and I heard someone describe it as magical once, and I kind of know what they mean now after having done some examples myself with a few little assumptions about a problem. You can make some pretty cool claims by doing this process of proving by induction. Some of the prior knowledge you're going to need to hopefully make some sense of this video is sequences and series, which we spoke about in Lecture 3, and telescoping series, which was our previous video. Now, I'll be honest, there's probably better places to have a look at proof by induction with simpler examples. We're going to do a proof by induction of a telescoping series, which is what we spoke about last time, and that's sort of just for my own understanding so that I could do one that I sort of came up with. Um, but yeah, if you want a simpler example of proof by induction, then there's probably other better videos to go watch. I can maybe link some below. In any case, the key concepts we're going to look at is what is proof by induction, obviously, and then we're going to do an example of proof by induction for partial sums. So let's jump into it and just explain firstly what proof by induction is. And essentially, there's 5 steps to it. The first step, or the 0th step, is to outline the proposition for some natural number n. Okay, so we're sort of outlining what it is that we're trying to show. And then we need to show that it's true for the first natural number, which is 1. Then what we're going to do is assume that it's true for some natural number k. And there. For prove it's true for some natural number k. So we're going to assume it's true. That's important. We're assuming it's true. And then we're going to show that it's true for k plus 1. So the next term after k, right? 1 more than k. And then conclude that p of n is true for all natural numbers n. So the sort of analogy that I think is important to draw here is a real life analogy. So if we look at something like this, imagine you're standing in front of a ladder with infinitely many rungs going upwards. To prove that you can climb onto any rung of the ladder, you need to satisfy 2 conditions. The first condition is that you can get onto the first rung. Okay, you can't climb the ladder unless you can get onto the first rung. So this is equivalent to proving the base case, showing that the first proposition is true for first natural number 1. And then the other condition is that if you can climb onto one rung, if you can climb from one rung to the next, then you can climb all the way up the ladder. And this is what we call the inductive step. And it proves that if P of k is true, then P of k plus 1 is also true. And then it's true for all natural numbers n, which is going to be sort of our conclusion. So I feel like, yeah, if these are the only 2 conditions that we need to satisfy, then we can prove a lot of interesting facts using proof by induction. So let's look at an example. Hopefully you can recall, and you've watched the previous video about telescoping series, but here it is as a recap. Let's just be clear in terms of the proof by induction step about what a proposition is. So if you look here, we've got 1 over k times k plus 2 can be broken down into partial fractions. And so, we get this as our result. So 1 over k times k plus 2 is 1 over 2 multiplied by 1 on k minus 1 on k plus 2. Okay, so what that means is that that's a proposition about a natural number k, right? So 1 on 1 times 3 could be expressed in this way because it is of this format, 1 on k multiplied by k plus 2. 3 is 1 plus 2. So you can sort of see the similarity here. Obviously, this is a specific case of this general instance, right? So that's sort of our first proposition, and what we need to do with our proof by induction is show that it works for the first natural number 1, right? So what we're actually going to do is we're going to come over and start doing our proof by induction. So let's just be clear. This method we used here for our telescoping series wasn't using proof by induction, but we could actually do this same problem using proof by induction. So if we come over here and go to the top, well, this is what we're going to do. We're going to prove proof by induction for partial sums. So we're going to outline the proposition, and the proposition is the same as before. proposition is that 1 on 1 times 3 plus 1 on 2 times 4 plus dot 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 all the way up to 1 on n times n plus 2 is equal to this, which is 3/4 minus 1 on 2n plus 1 minus 1 on 2n plus 2. Okay, so that's sort of our first step, which is sort of given to us. That's sort of our problem that we need to show, right? Okay, remember our first step for proof by induction is to show that P of 1 is true for the first case. So that means for the first case, with natural number n being 1, it's true. So let's take that situation. 1 on 1 times 3 equals 3/4. I'm just looking at the right-hand side here. Minus 1 on 2 times n plus 1 minus 1 on 2 times 1 plus 2. Okay, that's 1/3. The left-hand side is 1/3. The right-hand side, if you simplify things, you get 3/4 minus 1/4 minus 1/6, which is 4/12, which is 1/3. So we have proven the first step of our proof by induction, which means we've got our first foot on the ladder. Now what we need to do is assume that this holds true for some n, for some other value k, and obviously this is taken from before. It needs to be a k. So we need to show that it's true for some k element of natural numbers. So essentially we're just replacing n with k, right? We're saying this will also be true for some k. Just taking this line and changed it to k. Okay, and then what we need to do is show that P of k plus 1 is true. So this is just to show that we can get to the next step on the ladder. And so what we're going to get is this, and this is where it can be a little bit confusing, but let's just look at the left-hand side here. What we need to do is we need to go all the way up to k plus 1, okay? So just sort of maybe ignore the pink box for now, but we're taking this left-hand side, you'll notice, now goes all the way up to k plus 1, okay? The kth term is now the k plus 1th term. So the last term here, this k became k plus 1. This k here also became k plus 1, and it's sort of substituted into this last term here, which means the term prior to that has to just be 1 on k multiplied by k plus 2. So I think that should make sense. What was originally the last term was the kth term. We need to show that we can get to the k plus 1th term. So we need to add this extra term here. And essentially what we need to show is that it equals this. And you're probably wondering, where did this come from? Where did this right-hand side come from? Well, the right-hand side is just this, right? Which is what we're trying to show. So we're just going to drop the right-hand side for now. We need to show that the left-hand side does in fact equal that. Okay, so what we can do now is, now we think about this pink box. This first part, up to 1 on k times k plus 2, is just the right-hand side of this term here. It's just this part, isn't it? Because we're assuming that that's true, right? So we can use this right-hand side from up here and substitute it into here. But then we need to add on this term here. Okay. What we get is this. What we get is this. So we get this sort of line here. This line, we just need to recognize is equal to the right-hand side. And I encourage you to get a pen and paper out and show that this line here equals the right-hand side. But one thing you can do, if you just need to verify that something is true, you could obviously do the fractions and collect like terms and common denominators and all that stuff. But what you can do is you can just come over to Desmos, and you can see that this top line that we've got here is equal to this top line we have here, right? We can see that that's actually equal to the right-hand side, which is this second line. And so you can see if I turn one of them off that they're on the same, they sit at the same points, right? So that graph shows that this line equals what we're trying to show, which is the right-hand side. And so we can conclude that P of n is true for all natural numbers n. So by the principle of mathematical induction, it follows that P of n is true for every natural number n. So quite a challenging example, I think. As I said, there's easier examples of proof by induction out there, but I think this is a neat one because it sort of follows on from the previous video. Oh, it's hard to explain some of these things, but hopefully that made some sense. Good luck. I'll talk to you soon.